Hello. In this video, we're going to discuss briefly the operation of an IC timer circuit, specifically the 555 circuit. And I have drawn the pinout of the circuit and a simplified schematic so that we can become familiar with the circuit before we start looking at how to connect it in order to create different types of multivibrators. So first notice that the 555 timer has 8 pins. It has a ground pin, trigger, output, reset, control voltage, threshold, discharge, and VCC. Notice in the simplified version of the schematic that I have omitted the reset and control voltage pins. And the reason for that is to keep things simple. I'm not going to discuss that functionality, so we are going to assume that both the reset and the control voltage are unasserted, so connected to ground, and so they have no effect on the operation of the circuit. And if we ignore those 2 pins, we can see that in the simplified schematic, we have between VCC and ground 3 resistors in series, 3 5 kilo ohm resistors, which give the name to the circuit 555. And we can see that there are 2 comparators, C1 and C2. And those comparators are connected to the voltages between the resistors, which I have labeled as VTH and VTL. And because the 3 resistors are equal to each other, they basically divide the VCC voltage so that VTL is 1/3 of VCC and VTH is 2/3 of VCC. And so the 1/3 of VCC and the 2/3 of VCC points are fed into the 2 comparators C1 and C2. And then the other pin the other input of comparator 1 is tied to the threshold pin. The negative input of comparator 2 is tied to the trigger pin. And the outputs of the comparators are connected to an Aries flip-flop. And the idea with the Aries flip-flop is that it has 2 states. It's a bistable circuit. So when the R signal is high, is asserted high, then the Q output is high and Q bar is low. And when the S signal is asserted high, then the Q output is low and the Q bar is high. And notice that when Q bar is low, Q bar controls the Q1 transistor there that is operating as a switch. And so when Q bar is low, it basically turns off transistor Q1, so it will be in cutoff or an open circuit. And when Q bar is high, it will turn on transistor Q1. And therefore there will be a continuous path from that discharge pin to ground. And so I've summarized the operation of the circuit in the 2 lines that follow. Notice if you look at comparator number 1, that because of the 2 inputs, if the threshold voltage, which is externally applied, is greater than VTH, which is 2/3 of VCC, then the output of comparator 1 goes high, which means the flip-flop is reset in the reset state, which means that the output Q is equal to logic 0 or low, and Q bar is high, and therefore the output of the circuit is low, and Q1 is saturated, so Q1 is on. And if you look at comparator 2, we can see that when V trigger, which is the externally applied voltage, is lower than VTL, which is 1/3 of VCC, we have that the output of comparator 2 is going to go high, and therefore the flip-flop will be in the set state. So the output Q will be equal to 1 and Q bar will be equal to 0. And since Q1 is directly tied to the output, that means the output of the circuit will be high and Q bar is tied to the base of Q1. And so if it is 0 or low, it means that Q1 will be in cutoff for an open circuit. And so we're going to see how by connecting different external components to this circuit, we're going to be able to operate it as either a pulse generator, which is going to be a one-shot multivibrator, or a monostable multivibrator, or an astable multivibrator, which is basically a square wave generator or a clock generator. So let's take a look at the connections to configure the 555 timer as a monostable multivibrator, which is also referred to as a one-shot multivibrator. And notice in this modality, if you look at the little yellow box on the right-hand side, you can notice that there is in this modality an input signal, which is the trigger signal. And when that input signal goes low, meaning the trigger goes low, an output pulse is generated. And we can program the width of that pulse using external components. If you look at the circuit, I have redrawn the simplified schematic with the external configuration, and notice that it is just a 5x5 timer circuit with a resistor and a capacitor, and basically a trigger input signal. And then we have connected the discharge pin to the node of the capacitor to allow for a path for the capacitor to discharge whenever Q1 is turned on. So let's take a look at how this circuit operates to create a pulse at the output. We're going to assume the initial condition to be the stable state. The stable state is when the output is equal to 0. And if the output is equal to 0, that means that my flip-flop is in the reset state, which means that the Q output will be low, which means the output is 0, and the Q bar output will be high, which means that Q1 is in saturation. So the Q1 transistor provides a continuous path for the capacitor to discharge to ground. And so therefore the capacitor is discharged, or VC is equal to 0. And now let's assume that we apply a trigger signal. And when we apply a trigger signal, our trigger signal initially is high. And let's say I apply it at time equals t equals 0, just to make our calculations later easier. So at time equals 0, my trigger was high, and as we said, my capacitor was discharged, so the output, the voltage across the capacitor is low, and my output is also sitting at a voltage of 0. So everything is low. And now at time equals 0, I'm going to apply a trigger. And when I apply a trigger signal, that means my trigger pin goes below VTL, which essentially means that the output of comparator 2 is going to go high, because now my trigger is lower than VTL. When the output of comparator 2 goes high, that means the S pin in the Aries flip-flop goes high, and therefore my flip-flop is in the set state, which means the output Q is high. So let me go drawing these things so that we know. So we said my trigger is lower than VTL, therefore the output of my comparator is high. If the output of my comparator is high, I'm in the set state, and in the set state, my output Q is high, my output Q bar is low, which means my V out, since it's directly tied to Q, is gonna go high. So I'm gonna draw that. Oh, excuse me, my output goes high. My Q bar is low, which means transistor Q1 is going to be turned off. And therefore there is no discharge path for my capacitor. That path is basically cat over there. And therefore my capacitor is going to charge through resistor R towards VCC. And so my capacitor is going to do something like this. And I go charging towards VCC. But notice, as soon as my capacitor reaches, or the voltage across the capacitor reaches VTH and surpasses VTH, notice that at that point my comparator C1 turns on, or rather its output becomes high. I'm going to erase the other signals so that they don't disrupt us here. So now I have, again, my VC sitting at VTH, or slightly higher than VTH. So the output of comparator 1 goes high, which means the reset pin in the Aries flip-flop goes high, which means my Q is going low at that point. So whenever I reach VTH, my output of the flip-flop Q goes low, meaning my output voltage goes low. Q bar goes high, which means my resistor Q1 is in saturation, and it provides a continuous path for capacitor C to discharge. And so capacitor C will start discharging towards 0. And if I don't apply any other trigger signal, this is what I will have. I will have a pulse at the output. And again, this is called a monostable multivibrator because it only has one stable state, which is when the output is low. I can bring the output out of that stable state temporarily by applying a trigger signal. So the trigger signal is going to cause the capacitor to charge, but as soon as the voltage across the capacitor reaches VTH, which is 2/3 of VCC, then basically my circuit will reset itself back to its stable state, and the capacitor will discharge, and that will be it until the next trigger signal. Let's take a look now at the width of that pulse and how we can control it, how we can program it. And in order to do that, I'm going to move this qualitative analysis out of the way a little bit, or make it smaller. And now again, notice that the width of my pulse, I can refer to it as t by simply saying my pulse starts at time equals 0 and it ends at the time equal to t. So t will essentially be the width of my pulse. And I can do so by noticing that t is the time that it takes capacitor C to charge from 0 to all the way to VTH. So this is also the width of my pulse, which is equal to t. And so the equation for the capacitor charging from a voltage of 0 to a voltage of VCC is equal to VCC is equal, or VC rather, is equal to VCC times 1 minus e to the negative t divided by the time constant of the circuit, which in this case is RC. Now I can note that at time equals capital T, the voltage across my capacitor is equal to VTH. So VC is equal to VTH, which is also equal to 2/3 of VCC. And I can substitute those values into my equation above to come up with an expression for capital T, the width of the pulse. So I will do VC, which is VTH, or 2/3 of VCC, is equal to VCC times 1 minus e to the negative t, capital T divided by RC. And I can solve this equation for my capital T, and if I do that, I will end up with t being equal to RC, time constant, times the natural log of 3, which is approximately equal to 1.1 times RC. So basically with this equation, I can now select adequate values of resistance and capacitance in order to control the width of my pulse. And that's how the 555 timer can be configured to operate as a monostable multivibrator or a pulse generator. Next, we're going to see how to configure the 555 timer as an astable multivibrator or a clock signal or square wave signal generator. And notice in the little box on the right-hand corner, the little yellow box, that essentially as an astable multivibrator, we're configuring the circuit so that it has no input signal, it only has an output signal, and it outputs a square wave, which essentially goes from 0 to VCC. Notice in the configuration of the circuit now that I have included the 555 timer and one capacitor C and two resistors RA and RB. Now, if I assume my initial condition to be that my capacitor is discharged, my capacitor C, and my output is sitting at a high voltage, so if I were to draw this in my plots here, I will have my initial condition, my capacitor is discharged, so VC is equal to 0, and my output is sitting at a high voltage, which will be equal to VCC. And obviously my flip-flop is going to be in the set state because my Q is high, therefore my Q bar is low, which means my transistor Q1 is turned off. And if my transistor Q1 is in cutoff, then this path is cut, and so my capacitor is not connected to Q1, but rather is connected to VCC through RA in series with RB. And so what happens is that capacitor C is going to charge towards VCC through the RA and RB resistors. And so it's going to start charging. And at some point, my voltage across the capacitor reaches VTL. And notice when my voltage across the capacitor reaches VTL and increases slightly beyond VTL, the output of my comparator is going to go low. My comparator 2. But notice that this has no effect in the circuit because my flip-flop is already in the set state. And so the only thing this will do, this basically has no effect. It will have an effect once we are crossing in the opposite direction. So no effect, my capacitor continues to charge. And at some point it's charging towards VCC. At some point it reaches VTH. Now when it reaches VTH and it slightly exceeds the value of VTH, notice that the output of my comparator C1 goes high, and therefore my reset pin gets asserted in my RS flip-flop, which means my output Q is going to go low, meaning my output is going to go low at this point. And my Q bar goes high, and that basically saturates or turns on transistor Q1, and therefore now I have a path for the capacitor to discharge through Q1. And notice that in that case it's only going to discharge through RB. And so my capacitor is going to start discharging towards ground. My output has now gone low, and it's going to stay like that until my capacitor reaches a value of VTL. And once the capacitor goes slightly below VTL, notice that in that case, now the negative input of my comparator C2 is lower than VTL, therefore my comparator C2 turns on, goes high, the flip-flop gets reset, gets set, which means Q output goes high, Q bar output goes low, which means my output voltage will go high again at that point. And my Q1 transistor is going to be cut off. Therefore, no more room for the capacitor to discharge. The capacitor will start charging again towards VCC, and the cycle will start again. And basically, the capacitor will continue to charge and discharge between VTL and VTH, which is 1/3 of VCC and 2/3 of VCC respectively, yet my output will continue to go high and low. So let's perform now some calculations to figure out both the period of oscillation for my clock signal, for my square wave signal, as well as the duty cycle for the signal. And I have drawn the beginning of another charging cycle for the capacitor simply because the first charging cycle is not very representative because we're starting from 0. And so I'm going to consider my period of oscillation to be from this point to that point. And I'm going to refer to the portion where my clock signal is high as TH and the portion where it is low as TL. Alright, and so first let's consider the TH, which corresponds to the portion of the waveform VC where the capacitor is charging from VTL towards VCC. So first, to calculate TH, consider that C is charging towards VCC, and so the equation for V sub C is going to be equal to VCC minus VCC minus VTL, which is the initial voltage at that point, e to the negative t divided by tau, and tau in this case, since the capacitor is charging through the series combination of RA plus RB, is going to be RA plus RB times C. Now I can see that at t equals TH, I'm just assuming that this is my 0 point, the beginning of the charging cycle. So that's my 0 point there. So at t equals th, I have my Vc equal to Vth, which is essentially equal to 2/3 of VCC, and VTL is 1/3 of VCC, or VCC divided by 3. So if I substitute those values into my equation above, I come up with the following expression for TH. TH is going to be equal to RA plus RB times C times the natural log of 2. Or I can express it as TH approximately 0.69 RA plus RB times C. So this is my approximate value for TH, which is the portion of time that the clock signal is high. And now I can do a similar calculation for TL, which corresponds to the capacitor discharging. I'm going to assume my 0 point now to be the point where the capacitor is at its maximum value. So here is my new reference point. If I take that as my reference point, the equation for my capacitor discharging is going to be Vc equal, and its original value is Vth, its final value is Vtl, and so I will have my Vc being equal to Vth e to the negative t divided by the time constant tau. The time constant, notice that the capacitor discharges only through Rb, and so the time constant is Rb times C. And like I said before, at t equals TL, I know that my Vc is going to be equal at this point over here. So my Vc is equal to Vtl, which is essentially Vcc divided by 3. And my Vth in the equation above is equal to 2/3 of Vcc. So if I substitute those values into my equation above, I come up with an expression for TL that is equal to Rb times C times the natural log of 2. Or I can approximate it as 0.69 Rb times C. And so that's my equation there. And so finally, I want to use those expressions to come up with my period of oscillation, which is going to be TH plus TL. So my period of oscillation T is TH plus TL, or 0.69 RA plus 2RB times C. And that's an important expression. Notice my period of oscillation is dependent or externally set by the value of the capacitor as well as resistors RA plus RB. And my duty cycle, by definition, is going to be equal to TH, or the amount of time that the clock signal is high, divided by the overall period, T. And if I do those calculations, the 0.69s and the C's will cancel, and so I'll be left with TH, which is RA plus RB divided by RA plus 2RB. And notice that this is a quantity that can vary from 0.5 to 1, or from 50% to 100% duty cycle, based on the relative values of RA and RB. So we can see when RA is very small, the duty cycle will be approximately 50% duty cycle, and then I can go increasing RA to increase my duty cycle. And that's it. This is how you configure a 555 timer circuit as an astable multivibrator. Thank you.